this video, we're going to show what happens to our line current as we change our field current with a mechanical load attached. Okay, in the last one, the prony brake was attached to the motor, but it wasn't turned on. It wasn't producing any mechanical load. Now we're going to load that machine up to 6 Newton meters. We're going to start out with a field current of 2.5 amps, and then we're going to slowly decrease our field current and see what happens to our line current. Okay, and what we're looking for is, so we're going to start this out probably overexcited. We'll see our line current come down and then come back up as that thing starts to become lagging, and then we're going to see what happens if we lose the magnetic link between the stator and the rotor, and that machine drops out of synchronization. We'll see what happens to it. Okay, I'm not recording the RPM speed of a synchronous motor because it's either going to be 1800 or it's going to be way lower than that. And the only time it's ever going to drop below 1800 RPM is when we drop out of synchronization. And you will hear it, you'll see it. I'm not recording that value just because it is what it is. The speed is going to stay at 1800 RPM as long as it's in synchronization. That's just the way it is. Okay. Camera set properly here. Oh. Hopefully we can see those numbers. I know the DC ammeter is a little tough to read, but I will give you the values of it. You can see your line current. So starting out, we've got our switch closed across those that short out resistors for to see what happens with the or to get rid of the induced voltage in the rotor windings. Fire this up. It's running as an induction motor. We're at 20 current's dropping, starting out at 20. We're going to drop down to 10. We're going to energize our field, take our field up. The field's actually fused at 2 amps, so I'm going to put some load on this now. So that's 6 Newton meters of load. Bring our field current up to 2.5 amps. And we're seeing 12 amps of line current. I'm going to drop this to 2 because that's what it's fused at. With 2 amps of field current, we've dropped to 8.4 amps of line current. Drop down to 1.5 amps. So we're increasing our field rheostat to decrease the field current. We've got 1.5 amps of field current right now, and our line current is 5.5. Drop down. 1 amp of field current gives us a line current of 4.7 amps. Half an amp of field current, we've come back up to 7.4. And we'll see what happens when we take all the field current away. Got a line current of 12 amps. It's actually still running in synchronization. So this has got enough residual magnetism in it to maintain the load. We're drawing 12.2 amps. I'm actually going to do now, to show you what happens when we drop this out of synchronization, is I'm going to cut our field current down to next to nothing. And I'm going to increase the mechanical load on the machine. Watch that ammeter. And then it jumps up. And you hear it clunking and the speed jumping around. And then when we take the load back off, it reestablishes that magnetic link. So I'll just shut that right off. So if we increase the load to the point where you see our current slowly creeping up, and as I increase the load, it keeps going up slowly, and then when it drops out of synchronization, you'll see it just spike. So it goes up to 20, 21. Take the load off, it locks back in. Current looks, it makes this V right here. Wherever our line current is the lowest, that is when all of the current going to the synchronous machine is providing mechanical load. That's when the machine is running at unity. Anything before that, it's running lagging. Anything after that, it's running leading. Okay? And when I increase the field, we didn't get quite with the pony brakes, you don't get a great result because as soon as the speed drops down, as soon as it drops out of synchronization and the speed drops down, actually the mechanical load drops too, because pony brakes are based on inertia. So as soon as the speed comes down, it's not applying as much load as it was before, and that's why you heard that thing kind of clunking and banging and whatnot. It was dropping out of synchronization and then reestablishing and dropping out, reestablishing. Okay, those are mortar sewer windings. As soon as the main field started spinning faster than the rotor, you got a huge induced current, and those are mortar sewer windings, and they kicked that motor back ahead. Sometimes it relinked, sometimes it took a few times to relink. Some strange stuff was going on in there, but that's what happens if you break that magnetic link. Is that it stops running as a synchronous motor, starts running as an induction motor, and that's when you saw the current jump up to 21 amps, right? Like when we still had our link established good, even with 0 amps, it was only drawing 12 amps. And then as we increased the load, we saw it kind of slowly creep up, and then it jumped up to 21, and then dropped down, and it kind of bounced around. That's what was happening, is that motor was dropping in and out of synchronization. Again, not enough. If there was enough mechanical load on that thing, you could potentially stall a synchronous motor, especially if it was one that was made without our mortise windings, right? If you had a synchronous motor that was meant to be started with a DC machine to get it up to speed, and then you energize your synchronous your field windings, run it as a synchronous motor, and then take the power away from the DC machine, so it's just a synchronous motor, and you overload it, you would see the speed go from 1800 RPM to stalled, right? If it didn't have the amortisseurs in there, as soon as it dropped out of synchronization, it would basically stall. So full speed down to 0.